Hello, and welcome to my talk on optimizing Azure Databricks workloads. This talk is about how to improve your Azure Databricks by understanding lower level details of Spark. First, a little bit about me and my company Elastacloud. My name is Richard Conway. I'm the founder and director of Elastacloud, a UK cloud data analytics consultancy. I'm both an Azure MVP and a Microsoft regional director and have been for many years. We're an Azure Gold partner focused on cloud platform data analytics and winner of the OSS Partner of the Year 2015. In my spare time, I've been personally interested in building up communities, so I founded the UK Azure User Group, the IoT and Data Science Innovators UK, the Cloud Infrastructure User Group and Data Science London. All of these you can join on meetup.com. In the past, I've contributed to the data science degree program at academy.microsoft.com, and one of my passions is teaching children software development. So I established Azure Craft, which is an annual conference which teaches children how to use things like Raspberry Pis, do Minecraft programming. In the past, we've partnered with Microsoft Research and done things like try to teach the kids AI. I'm a contributor to several open source projects, Apache projects, including Storm, Spark, Apache libcloud and Parquet, and several others. You can see them on my GitHub, which is github.com/azurecoder or /Elastacloud. And Elastacloud has about 70 people across London, Nottingham and Spain. So what is the agenda for today? We're going to have a quick recap of Spark and of Azure Databricks. We're going to talk about things like shuffling, sorting, and partitions in Azure Databricks. These might be foreign concepts to you, but you'll begin to understand them quite quickly. Then we're going to go through optimizations. You may have heard of the Parquet file format. Parquet is a fantastic format for big data for a number of reasons, and I'll go into different ways of using it, different ways of optimizing through it, and things that will stand you in good stead going forward. Then I want to talk about compute and building optimization into notebooks, where we have pain points and where we have problems, and some techniques that you can use to be able to analyze some of your pain points when you have slow moving workloads. Lastly, I'm going to touch on Delta Lake, or Databricks Delta, which is inbuilt into Azure Data Lake, even though Delta Lake itself is an open source library. So let's think about some of the key features of Spark. So Spark operates by sending commands from a driver program to worker nodes. Each of these worker nodes have programs on them called executors, and within the executors, they run tasks. The driver, if you like, is really something which sends distributed instructions to the workers on the Spark cluster. One of the key things about Apache Spark is the idea that you can have multi-language semantics. So in the early days, Spark was only usable if you had knowledge of Scala and Java, because it's built using Scala via the JVM. Later Python was added, and then later within Apache Spark 2, the Catalyst engine Tungsten was added, which allowed you to write SQL. And what this meant was that everything got compiled down into a sort of intermediate language, which allowed Python, Scala, and SQL to operate in exactly the same way. Later on, R was added, and you have tools such as Spark R and different tools from R environments, which really help you to get to grips with using the Spark APIs from R. So Apache Spark is a distributed framework, and it works by sending instructions from the driver program to each of these worker nodes, which are called executors. And that means that you can have hundreds or even thousands of tasks, depending on the number of nodes that you have, running across the cluster. The Catalyst engine, as we said, builds something called logical plans for all things that you execute. And you'll find talk within Spark of something called a direct acyclic graph, or a DAG. And what this will do is it will break down the set of instructions, and it will allow you to execute some iteratively in a serial manner and some in parallel. A lot of people in the past have called Spark the Swiss Army knife of big data, and that's really because of the number of features. In the heyday of Hadoop, you had a key technique called MapReduce, which took all keys and mapped them down to a set of pulled them out of data, and then allowed you to reduce on those keys. So you could count, you could sum, you could do lots of different things within your reducers. But map and reduce functions allowed you to distribute the workload across different nodes and then bring them back together to give you aggregated results. Spark improved on this because it allowed distributed in-memory data sets and specifically caching, which meant that you could run workloads much faster by utilizing the cache in Apache Spark. And what that meant is that rather than writing to disk, because I/O on disk is quite expensive, you could store your results, intermediate results, in memory. And then rather than start executing at the beginning of the DAG every single time you executed an instruction, you would just fetch the latest results from memory. The other thing is that there's an ability to run on lots of distributed models. So, for example, you can run on Kubernetes. Many people at the start of the Spark revolution were running on Mesos. You have HD Insight, which runs on Yarn. And you have a standalone version of Spark, which Databricks uses. Okay, so we talked a little bit about Spark, but let's think about Databricks. So Databricks gives you a lot more power over standard Spark out of the box. The key feature, as you can see in the image, is the idea that we can run notebooks and notebook cells. Really, really powerful. It gives you this sense of usability where you can just execute functions. You can execute anything that you want. You can use Markdown. You can put results on the screen, and you can effectively go through your notebook bit by bit as if it was very procedural. The important thing about Databricks is that it has a set of APIs which allow you to automate. So every notebook can effectively become a web API endpoint, which means that you can call this from Azure Data Factory, you can call this from an Azure function even. Inherent in Databricks is security. Spark natively actually doesn't really come out the box with security, although there are some Apache Foundation projects which allow you to add Kerberos to it. But by default, Databricks allows you to log in using an Azure Active Directory token, and it recognizes who you are through this, which is very, very important because as a result of that, you can filter down, you can add permission sets, all kinds of stuff against your Azure Active Directory login. Whilst most data is unstructured, and you might read it from a storage account, a data lake, the local file system, HDFS, you do have the concept of databases and tables. We won't be covering this in this talk, but it's incredibly useful because you can effectively create a logical model on top of sets of files, and then you can create permissions on the tables themselves, which allow you to sort of hammer down the permission set so that certain people can read tables and others can't. And both of these are fully compliant with Databricks APIs. Unsurprisingly, because this is a first-party product in Azure, there's very, very tight integration with Azure. It's a platform as a service offering, and that's great for us because it means you click a few buttons, and within a few minutes you have you have an Azure Databricks cluster and a set of notebooks. On top of this, you have what we call a multi-user collaboration environment, which means that I can work on notebook cells, I can work on the same notebooks with my team, and in real time I can see these changes appear on my screen. I can see things executed. So it's a phenomenal collaborative environment for both data scientists and data engineers alike. So the first thing we're going to look at is different data formats, and we're going to go from the premise of what it's like to have very, very unstructured data formats. So you can see on the right we've got text files. If we take a look at a text file, we have a collection of words. There's no real structure to it, so we can't parse this easily. We have to write functions to do this. So it takes quite a lot of work for the CPU and CPU cycles to write our own parser. Then we have unstructured data like CSV, and we'll find that there are quite a lot of CSV parsers. It's very, very easy to look at a CSV file, work out whether it's got a header or not, understand what the general structure of the CSV file is, and even though there's no hard and fast rules that we can guarantee with a CSV file, because there's no compliance. If the CSV quality is okay and it has integrity, then we should be able to read this in without writing our own parser. Then we have the idea of JSON. JSON does have compliance. You can run a JSON document through a JSON linter and work out whether or not it's structured or not, and following sets of rules. So we call this semi-structured because we can pull out attributes, we can pull out arrays, we can infer type from this by the fact that numbers, for example, are not in quotes, whereas strings are in quotes. Then we have Parquet. Parquet is a highly portable structured file format. So Parquet allows you to carry the schema with the data, and we'll be looking at the structure of the Parquet file and quite a lot about optimization with Parquet, because it's an incredibly important facet of using Apache Spark. But as you can imagine, that means that we understand from the Parquet schema whether or not things are nullable, whether or not fields are numeric or dates or strings or booleans, and as a result of it, it allows us to have a very, very compact form which we can store really efficiently. So I just want to focus a little bit on how data moves around a cluster, and I read this explanation from an old Spark and AI summit, and I thought this was a really good depiction of shuffles and sorts, which is a concept that you'll need to understand when you start using advanced Spark workloads. So if we have two tasks, what ends up happening is we can map data to various nodes, and we'll call them nodes. We'll call them nodes 1 and 2 for now. And what essentially happens is each of these, let's say we're categorizing or we're filtering or something, and we need to have 3 different things written out. You can see we've got different measures of 1, 2, and 3, and we'll call this an intermediate domain. And so what will happen is we'll pull these out and we'll put them on the same place, but on single nodes. And the problem is we have to pull all of these together, because on the first node where we do the shuffle right, we have 1 and 1, and what this essentially means is that we've got 2 lots of 1 that we need to bring together, just like we've got 2 lots of 2 and 2 lots of 3. In order to do this, we have to reduce this, which is to take all of the 1s, put them together on the same node, take all of the 2s, put them together on the same node, and take all of the 3s and put them together on the same node. So these 2 activities and these 2 distinct stages are called shuffle writes and shuffle reads. And what we'll find is that they add latency onto the job, onto the Spark job, So it's really important that we understand this, because we'll continually need to optimize shuffle writes and shuffle reads. We're going to take a quick look at the Parquet file format, and this is taken from the Apache website. You can see that we've got a Parquet file which has the magic number at the start, which is the beginning marker. Then we have a few concepts here. We have row groups, and the row groups by default contain a certain number of rows. In Parquet code that I've written from scratch, we've set these at 5,000 rows, but you can set these at different values. Then we have what are called column chunks in there. So because Parquet is a columnar format, what happens is we put all of the columns together. So all of this is about column offsets. And so within each column chunk, we have pages, and these pages allow us to have things like repetition levels. So, you know, are column values repeated? Things like definition levels, where we can understand effectively how we're going to encode these, and all of the values themselves. So from this, we can end up with a highly compact protocol, which uses the Thrift protocol, which is a well-published standard. The interesting thing about each page is that the page itself can be compressed. So in the file, you can see that we have the rows, columns, and pages, and you know each row is a numbered row group. Then at the bottom of the file, we have a footer which contains all of the file metadata. So that would contain the version, it would contain schema, it would contain key value pairs, but it would also contain encodings. So for example, some of the encodings that we can put in strings are dictionary encodings, and what this will do is it will allow us to store indices of the different strings, so that we effectively have nothing more than an index within the actual column values rather than the entire strings, and how often that they're repeated and their position. And then we can apply further improvements to this, specifically so that we can take those values and we can do something called bit packing, which will allow us to go from bytes to bits very quickly, so that we can effectively just have a dictionary that contains the minimal amount of storage. What I'm going to do now is I'm going to flip over to my browser, and we are going to take a look at a set of notebooks, so that we can demo and explain everything. Okay, so here we have our Databricks cluster, and I'm going to go to my user folder here, and we'll start at the beginning with this. Now I'm just going to show you from Storage Explorer quickly, and we'll go through all of this data as we go along. But what I've done is I've downloaded in raw form Wikipedia page counts from just one day for a few hours in August 2016. So there's around about 3 gig of data here. Later we'll also be looking at New York taxi cab data for January 2016, and also we've got Alice Through the Looking Glass by Lewis Carroll as well. Okay, so the first thing that I'm going to do is I'm going to run this, which will automatically mount the data lake that we just saw, that we went through. And whilst that's going on, because it will take a couple of minutes, let's go through what the data looks like on the Wikipedia page counts. So it sort of looks like this. we've got a space separated file here. You can see in the first column we've got a code here, and then after that the second thing is actually the name of the page. So you can see here we've got fr.b is the first one, then special recherche Achille _ Paraguay. Then the third column is the number of requests. So how many times was that page requested and by whom? How many times was that page requested? And then the fourth column is the number of bytes as well. So we'll find that that this gives us all the information that we need to understand the number of page counts. So we'll be doing our own counts and sums and maxes and mins on this in a second. So so we can still see that this is taking a little while to run. The script goes through unmounting and then remounting of this. Now, we'll start first of all by using what's called the RDD API. So the RDD API are resilient distributed data sets, and effectively they were what you had to use in Spark before version 2, before all these nice data frames and data sets which we're all used to now in Spark SQL. So just talking through the code, we see that we've got what's called a struct type, and I do apologize for all of those that are not used to Scala. This is a Spark API, so if you've used Python before, PySpark will look very, very similar to this. But you should be able to understand it and get the gist of it. So first off, we've got the code value, then we've got the page, then we've got the number of the request count, and then we've got the actual count. Now you can see, even though these last two are numeric, request count and count, I've called them string types, and that's because RDDs effectively split everything as a string. Then we've got this reading this in, and you can see here that we're using a protocol called WASBers, which is the access protocol for blob storage. Because this is not really a CSV, and we're doing this in a slightly different way from using the CSV provider, just to show what it's like to parse unstructured text. We split everything by space, and the mapper here gets each of these lines through, and then we pass this in through an array to create a row, and then from this we create a data frame, and then we can execute SQL statements like code, page, request count, and then we can count this. So let's run this and we'll see what happens. So you can see we're running a Spark job now, and if we go into that job, we can see that there's 9 tasks running in this second stage, and where it says 9 running, it means that they're all running concurrently as well. So it should be done quite quickly. There we go. And we should get a count, and you can see here that right at the bottom it says res3 long. That's 5 million. Oh no, that's 55,840,416. Right, now we've turned this df1 into a data frame. What we can do is we can write this to storage using the inbuilt Spark CSV provider. So I should be able to look at this and see a CSV folder emerging. Let's take a minute. And it helps to make sure that everything's going on. Again, we've got 9 tasks running currently. There we go. And we'll flip over there, and we created a staging folder, and you can see we've got CSV, and lo and behold, each one of these is 325 meg, which is more or less the size of the the 3 gig of files, more or less 2.73 gig of files. Okay, so this is gone from space to CSV now, and you can see that there's 9 of them, just like there were 9 tasks. Okay, so let's go back here, and we're going to read in the CSV and parse the schema. And one of the things that we'll do is we'll look at the amount of time that this has taken. We've just created this in the folder, and it tells us that this took 5.45 seconds to get that count. Now, you can see in this next cell, rather than use the struct type here, schema 1, which has got a string type for code, a string type for page, an integer type for request, and an integer type for count. What we're going to actually do is we're going to infer the schema. And when Spark infers the schema, given that we didn't create a header to these files, it didn't know what the column names were. So what it's done automatically is given us some column names of underscore C1, C2, and C3. So we're going to rename those columns, and but you can see where it says option here, we're going to infer that schema. So let's run that. Okay, now that took a bit longer. That actually took 3 times as long. That's 15.55 seconds. And part of the reason was that it had to scan the files initially to work out the types of those files. And by doing so, we had to do type inference. So, you can see, one optimization that we can do very, very easily is to define the schema. And schema in Spark is all important, because if it has to do inference and it has to work this out itself, it takes longer, as you can see. So now what we're going to do is write this back into Parquet. So we'll take the data frame which we just created, df3, and write that back to Parquet. One thing you'll notice is that this took 9.27 seconds. When we did the same thing with the CSV, you can see it took 32.58 seconds. And that's really the power of Parquet, because we're writing a lot less data there. And we'll take a look at that output now. So let's refresh this, take a look at Parquet. And first of all, we've got a lot more files. We've got 52. And each one of these is slightly different in size because of different tasks. You can see one of them is 1.4, so they're not quite balanced, which is important. It's a concept that we'll look at later. But there's also far less data because of the compression, the encoding, all of these things. Right, now what we're going to do now is read this back and do the count on the Parquet. Let's see how quickly that does it. Right, 5.55 seconds, okay? So pretty quickly, we're going to just run this again, and much quicker, 1.94 seconds, okay? Because it understands the schema already. Right, now that we've done that, we're going to look a little bit at Parquet Compression. We don't need to remount our data lake because it's already mounted. So we will read in the Parquet that we've just created. Let's see. It's going to take a minute just because each notebook has to attach to the cluster itself. So at the moment, our previous notebook was attached to the cluster, but this one hasn't attached yet. So hopefully it won't take too long. and very soon it should just be able to read in the Parquet. The goal of this notebook really is to understand compression and to understand that there are good and bad formats for using Parquet. The default really is a compression called Snappy, and one of the things that we'll do now is just write this as uncompressed and read it back in. Okay, so we've taken our previous Parquet data frame and we've uncompressed all of this. It's in memory now in Spark, and we're going to read back this uncompressed. Okay, and that took 1.74 seconds. Okay, now we're going to read back using Snappy. So Snappy is a Google compression algorithm. It's incredibly powerful, but it's also very lightweight. So you know, it doesn't compact things as much as other compression algorithms like LZO and Gzip. So you'll have slightly larger file sizes, but it will take less time to decompress this. Okay, so right, and you can see that Snappy was actually slightly faster than this. It was about looks like less than half of the time it took to read in the uncompressed Parquet, which is really important. So that's why Snappy is really the norm here. Just for completeness, we're going to take a look at Gzip Compression as well. So we're going to create this using Gzip. And remember, with Parquet, the compression works on the basis of pages. So we're actually compressing lots of different pages. You can see this was still a little bit quicker than having it uncompressed, but whilst our Parquet Gzip we'll be able to store this more optimally, and we can take a look at the file sizes now. So we looked at uncompressed, and we're looking at like 50 meg file sizes for that. We looked at the standard, and this is Snappy's like 25. So you know, in the largest files we've got less than half. And if we look at Gzip, you can see we've got more optimization even, and you know, 20 meg instead of 25 meg from Snappy. But the result is that whilst the storage is less, the compute that it takes to decompress each page is more. Okay, so let's crack on, and we'll take a look at Parquet Statistics. Now, statistics are incredibly important because what they do is they allow us to push predicates and really understand very, very quickly what you know, whether or not Parquet, some of the results that Spark will bring back. So we'll read in the Parquet first of all, and if we display this, so let's actually look at the data. We can see that we've got our code, we've got our page, we've got a request count, and we've got a count. Now the thing is, the Parquet is really good at storing metadata, and some of this metadata is request counts and counts in this case. And we might want to know things like maxes, mins, the counts for each page or for each code. And one of the things that the page allows us to do is to store that metadata. And that means that when we scan and we push predicates, Parquet will be able to effectively skip pages where it needs to, and say, you know, the max value is not this, or the min value is not this, it doesn't fall in this range. So it's great for not scanning the whole file itself, or all the files. So if we go and get the maxes and mins here, you can see it takes about a second, and we can get both the maxes and mins. then one of the things that we'll do is we'll use this spark.sql.parquet.filter_pushdown, which is a config setting, and we'll rewrite the Parquet effectively without statistics and then try the same thing. Okay, that hasn't taken long, about 5 seconds. And what we'll see here is that we read that back and run the same query on the min and max statistics, and it takes a little bit longer. It almost takes twice as long. With larger data sets, you'll really see the weight in this, and that's because it needs to scan everything in the file now, because we don't have statistics at each Parquet page to say these are the maxes, these are the mins, so it has to work it out itself using compute. Then the last thing is turning on and off dictionary encoding. So using those encodings. Dictionary encoding is really powerful for strings. So we've got that running in 1 second, and we have it running with dictionary encoding in almost half the time. And dictionary encoding, if you remember, was the concept where with strings or with exact values, like in this case we're doing a predicate for request count equals 13, this will be part of a dictionary and with repeated values and all of these things, and so immediately that predicate gets handled differently when you enable or disable dictionaries. Right, so we're going to take a look at some more things now. We're going to take a look at partitioning with Parquet. And partitioning, if you've we have to wait again to attach the cluster. But if you've been doing production workloads for some time with Apache Spark, you will know that partitioning is absolutely key. It's really important to prepare your data sometimes in the views that you want to look at with the data. So in this case, we have we're looking at the creating partitions from the Wikipedia data, and what that will mean, as we'll see, is that where we choose our partition field, it will create folders on that basis. So let's take a look at partitioning by request count. So what we would expect here, and we'll take a look at this while it's going on, is that here we go, Parquet with partitions, right? You can see that we have a whole set of folders with request count equals 1, equals 10, 11, 12, and our Parquet files will be in there. And you can see they're quite small files as well, so you need to be very careful with partitioning, because you could end up with a small files problem, which will take lots of I/O. So let's wait until this finishes. Got a lot of concurrency there. Okay, fantastic. That's nearly finished. Now we'll do an exact query here, which is to look at the to run a where clause where request count equals 19, and we should see that this is actually within the folder request count equals 19. So the scan that it has to do for this query when it builds up a plan is actually quite quick. So let's run that. You can see that partitioning this, I created a long time, and that only took 2 seconds because it found the folder quite quickly. We don't have a huge amount of data here, but if we had a lot of data, having that view in advance would be really powerful. So there we go. We will run that again. And this time it took about 5 seconds. Okay. So now what we're going to do is we're going to change the partition key, and we're going to partition by code, which is a string value. There's about 10,000 different codes we should see. So again, we've got a lot of concurrency, 48 tasks running in parallel, and we've got enough capability in the cluster to run all this parallel activity. There we go. Nearly done. It's just that last bit right at the end where wherever it's writing, all of the tasks are finished, and you know, the compute's done, the task is done, but it's still writing those files. So there's a little bit of lag, but it's not too bad. Okay, so now we've got code written. What we're going to do is we're going to display the code count there, and that took to do that aggregation, which was to group by the code and to count the number of codes. That took about 2 seconds. So we've created, and that's just using the normal Parquet without partitions. Right, now we're going to do the same thing, but we're going to use this with partitions. Okay, and it took slightly more time there, you can see, because there are 10,000 different folders that it had to scan through, which it didn't beforehand. Now, if you can imagine, there's a fine balance about making partitioning optimal. Then let's run this. Let's run this briefly. We can repartition by number. So in this case, we've got 10,000, and what this will end up doing is it will create us 10,000 files. And you can see in the task that even though it's running quite quickly, 10,000 files is a lot of files. It will eventually write this, and we shall see in here that, yeah, it's gone over that 1,000, but you can see here the files are getting smaller and smaller. Not great, not really optimal for us, so we probably want to avoid things like this. And then when we run that aggregation again, we can see now that it's doing a lot of work. It has to scan these 10,000 files. So there's a bit of concurrency, even though that all of these things have taken 5 seconds, more or less. Elsewhere, we're reading a lot of small files now as a result of this. So it's got the same result, but it's taken about 30 seconds. Then similarly, we've got this running for 10. And we should see that it's now got 10 files, and so we're back to being quite quick with 2.5 seconds. We're going to skip this, but as you can imagine, 100,000 files is going to literally keep the average file size to about 20K. We're going to have a huge I/O bottleneck here, so we need to be incredibly careful of this. And then lastly, I'm going to show you something about that single file, which is important to think about as well. So we had 10 files take about 5 seconds. We're partitioning, repartitioning. We can also coalesce, slightly different techniques. You might have seen the coalesce keyword, that works. just as well as the repartition keyword here. But you'll see that will write a single file. And so we should have here like a single task which is running, and that should finish shortly. Let's see how it's doing, physically doing. So we've got by 1. Still hasn't written yet. Okay. Let's give it a few more seconds, and hopefully soon we'll see that we have a single Parquet file. There we go. And if we look here, yeah, we can see we've got a file of 1.1 gig. Okay. So we're going to read that in and run the same aggregation, and you can see it was pretty quick. It was slightly quicker, I think, than the 10 files. The important thing here is that with a single file, the Parquet footer builds up quite large. So 1.1 gig is not huge, but the moment that you start to get into Parquet files of hundreds of gigs, it can be an issue. So we'll go back to the original just to compare it, and you can see that slightly different from 2.5 seconds to 1.85 seconds. So that default splitting up of Parquet files with the default number of partitions, which is normally 200, but it really depends on what the Spark optimization is, works better here. Okay, we're going to touch on Data Lake now, Delta Lake, and if we look, we're going to read in the New York City yellow cab data, which is in a CSV format, so we can use our CSV reader. Still attaching to the cluster. Okay, it's about 1.7 gigs of data. Over 1 million events of when New York taxis pick people up in January 2016. Now there's a couple of things here which were Kaggle questions. The first one is, what was the location of the most number of pickups made by yellow taxis? We're not going to be looking at that question because it requires a geospatial analysis, and I haven't installed the libraries in this cluster. And then the second one, which day of the week has the most number of trips made by yellow taxis in January 2016? Okay, so let's wait until that finishes. We'll start the next one. And whilst that's running, let's just take a look at the data. So we have a vendor ID, which I guess is a cab company. We have a pickup and drop off time, passenger count, trip distance, and the lat and long. And you can see there's more fields in this as well. Extend that a little bit. And yeah, including the amount paid and other things. So what have we got here? We've got the day name between 1 and 7, 1 being the start of the week, Sunday all the way to Saturday. and we've just ordered. So day 6 is the highest number of journeys, which is nearly 2 million journeys for the month of January. Okay, you saw that query, it took 30 seconds. Right, now what we're going to do is we're going to use Databricks Delta, which is, and whilst this runs, Delta is essentially it's an open source library, and it allows you to optimize around Parquet. So Delta will write everything that we've done by Parquet as well, and you can see that we can partition, so we can create specific views, and I've used this day name column to bring the day of the week so that we can run the same thing and try and understand whether we can get this faster. So remember beforehand, without Delta it took 30 seconds. Delta has lots of amazing concepts. It has an optimize keyword which tries to optimize the file sizes of Apache Parquet. It also has a Z order keyword which also allows you to create a specific order within the Parquet files within Delta. And Delta specifically is meant for being able to add add data as if it was a log. So let's just take a look at that. Okay. And whilst that's running, we're just going to flip back to our slides and we're going to have a recap and just some things that we're going to learn again. So Delta Lake is this. We have a very, very common pattern now within a data lake, which is to ingest data in bronze, to refine this data into tables, into something that's staged better, and then to pull out the views and features in this aggregate data store, which is called gold. And then this is how this will fit in with the Azure ecosystem, governed by Azure Data Factory, so the orchestrator, and Databricks is there at every point, and it can be served through Synapse Analytics or ADX, Azure Data Explorer. So we'll look at performance tuning. We've got the determination of the best type of serialized RDD. So RDDs underlie the data frames, and they can be either Java or Cairo, and each of these is either compressed or it's non-compressed. So they have different attributes, and depending on the size of your RDDs, you can choose different serializers at low level. Caching generally must fit into memory, so we haven't touched caching in notebooks, but it's very, very important that that doesn't spill over onto disk because it will slow down. If you've got a high turnover of objects in Spark, you keep creating lots of different things, then the garbage collector is doing a lot of work all the time and will slow down your applications. So you can tune this in different ways depending on how much memory you've actually got in your Spark cluster. Don't use nested structures to avoid recursive lookups within the nested structures. So use smaller objects and relationships. An obvious thing, especially for people with a data background, use numbers for keys and not strings. So we tend to use data structures, and we've looked at schemas and not objects like Scala objects. We could use arrays of primitives, which are pretty quick. And if we use serialized objects, these will equate to 1 per RDD partition, which is how data gets partitioned across the cluster, which means that each serialized object is not 1 per task, it's 1 per partition. You've got execution memory and storage memory, and you need to mediate between these. Execution memory is the heap objects that Spark needs to create. Storage memory is the cache that you save. Use the unpersist keyword where you can to remove cache, because otherwise you end up with storage memory saturation and you can run out of memory. We've talked about partitions, and we can dynamically set these. The default is 200. And we need to use predicate, something that is searchable very, very quickly, that we can push down, so date times, numeric, things like this. There's some guidelines I'll leave you with. Avoid using user-defined functions because Spark SQL has its own functions. The Catalyst engine has an expression class which we can extend, which is much better. Avoid using aggregate functions as well because of the way that they're interpreted by the Spark engine. Visualize the DAG with something called execution plans. We need to find bottlenecks in execution and reduce the number of steps where possible. And we need to understand the use of caching and understand that cache fraction actually puts things on disk. So it's really, really important to go to the Spark UI and see how much stuff has actually been cached. Cache intermediate results where we can, to stop the DAG from executing over and over again. When we're unable to write to the cache, we should use intermediate domains. And in the past, I've written these out on disk as Parquet and then read them in again much faster. There's an advanced concept called broadcast joins, and this will allow us to push small data frames to different nodes on the cluster where we can effectively use events in our code to grab these broadcast joins and then just do joins on them, so that for each node you'll have a data frame being sent to it. It's efficient, it sends a read-only copy to each node rather than every task. Let's just pop back to here and we're going to just quickly run our Delta queries. And you can see how quick that was. That took 2 seconds instead of 30 seconds. And we're going to run this and we're going to take away the partition. So yet again, this might take a minute or two. If you remember, in the previous query, we partitioned by day name, which we created, which was the number between 1 and 7. What we're going to do is we're going to use a feature within Delta Lake, which will allow us to optimize this table. And hopefully this won't take too long, but you can see we take this SQL-esque view, and so we drop the table if it exists. We create the table at the location which is on the lake here. Oops. And we should be able to just optimize this table, which will take the number of files in this directory and it will optimize it. So there won't be huge skews and biases in the size of each file. They'll be more or less the same size, and that's a great thing because as we spread activity across many tasks, what we'll find is that some tasks will need to run longer because the files that they're processing are larger. So avoiding that completely is key for us. Okay, we'll take a look physically on disk. And Parquet Delta non-partition. So it still hasn't written anything yet. Hopefully it won't take too long. There we go. And we're going to run the optimization now. And with best laid plans, that unfortunately didn't work, but essentially we're creating something called a Z order, and you can see that there's been a slight change to the table, but now what we'll do is we'll run the same query in SQL, and you can see how quick that was. So we didn't have any partitions, and it still took on less than 2 seconds, actually over 1 second. So understanding how that Z order works within Delta is all important. Anyway, I hope you enjoyed my talk. Thank you very much for attending. All of the notebooks will be made available along with the slides for you to try these things on your own. Thank you.